Good afternoon, class. I'm Renkai Xu. So welcome back to the SAR online course. And this course is supported by TSU, the Taiwan Space and Union. Today we are glad to invite Dr. Chih-Heng Lu to lecture about the application of SAR. Dr. Chih-Heng Lu, he received his PhD degree from the Graduate Institute of Applied Geology of National Central University in Taiwan. Now, he is the researcher in the Research Center of the Environmental Change of the Academia Sinica. Dr. Chih-Heng Lu interested in observation of surface deformation with SAR imagery and the data fusion of multi-spatial temporal resolution and monitoring the hazard distribution of the urgent image. So today's topic is the land subsidence monitoring. So let's welcome Dr. Chih-Heng Lu. Dr. Lu, please.
Okay, thank you. Thank you for the introduction. I'm happy that today I am come here again and to share some research. And today my topic is the. Wait a minute, I will share my. Yes, today I will speak about the land subsidence monitoring. So if everybody you already learn about a lot of knowledge about SAR. So right now we will continue to some advance about like the SAR process method. So reviews we have maybe like the flow detections or like some earthquake observations and maybe some other application. But right now we want to measurement like the slow movement of the on the surface. So we will use like the time series method, just like I my short outlines. So I will separate 3 sections. First is land subsidence hazard. The second is the multi-temporal InSAR monitoring, and I will introduce some method. And the third is soil compaction theory, because the most serious land subsidence caused by or induced by the groundwater pumping. So I will introduce some theory and make us know how the groundwater withdraw and cause the. Okay, so let's get back to the slide. Okay, the land subsidence, some people may be thinking about like the groundwater pumping cause the land subsidence, but it's like the slowly. But some case like the sudden event, like the Great Rift Valley is in the eastern of the Africa. Here is the 2005. They have a big earthquake because it's here is a normal fault, so it's like land subsidence. The left corner here is the show the field surface data, the pictures, and then tell you how the land break and the subsidence. And then the right side is pictures is very famous photo in the land subsidence. It's take from the Chih-Heng Valley. If you found the numbers, the top number is 1925. And this man stand here is 1967. So this means during almost 50 years, this pole from here become here. So this dropped or this descend almost 8 meters. It's a quite serious land subsidence. So the land subsidence is quite a serious problem about like the national lands development or national land security, and also the people's life and then their money. So in the world, a lot of cities face this problem. Here shows more than 30 cities, maybe more than 50 cities. They have faced this problem. Yeah. So from the USA to the Western Asia, in China and in the Vietnam, they have faced the problem, and in Taiwan is here. But previously I say the national land security, just like here is the Indonesia. The capital is the Jakarta. But this problem is when the land subsidence very serious, and then the people is very full of people in these cities. This country think about they should move their capital to new place is called Nusantara. I hope I pronounce it correct. Yeah, Nusantara. So let's make us should be face the land subsidence issue or in all the worlds. So how to know land subsidence problems? So we need to use some tools to measurement this deformation. So here list we call it from the air to the ground. It can separate the 4 kinds of the technique. From the airs, or we can look from the space, we can use the InSAR technique and then the GPS data. And on the surface, that we can use the leveling surveys to measure the vertical displacement. And then in the subsurface, a new technique is we call the compaction monitor wheel. It will record the different layers level of compaction. So we will know layer 1 compaction, how much centimeters decrease, and then so long that we can know the holes may be under surface 4 meters, and how much displacement in this area. And the other is groundwater monitoring well, that will tell us how the groundwater levels change. And then the table will show you the accuracy and the frequency and the spatial resolution. For the best is the compaction monitor well, because it's actually record the layers, or we call the source compactions. But its measure frequency cannot be every day or every hours. So it's about 1 month that we can get once. And every wells, the distance should be 5 to 10 kilometers. It is somehow not density in the subsided area. So another method is like the called the technique is the precise leveling. The accuracy is a little bit worse, but I think it's quite good because it can become a millimeter quality. But the frequency is every year they got once data. The frequency is too low, but it is spatial resolution is better than the compaction monitor wheel. It can become maybe 1 to 2 kilometers. You can get one benchmark. And the third technique is GPS or GNSS. I believe everybody already know that this technique. The accuracy in the vertical maybe just 10 to 20 millimeter, but the horizontal is quite good. Maybe can become 5 millimeter the accuracy, and the frequency can become every second, or it's the best. Mostly we will use every day's average results. But it's it's more expensive, so it's not can build everywhere. So the spatial resolution is not the good. It's almost 10 to 50 kilometers. The last is our will show you today is about the InSAR. Its accuracy is about 10 millimeter, or somebody will 10 to 20 millimeters accuracy, and its frequency is every 6 days. You will say it's very high frequency. I think it's maybe not, but it's enough for look for observation like this slow movement surface deformation. And the spatial resolution is really good. It's meters, 20 meters or 10 meters spatial resolution. So we want to use the InSAR, this technique. But previous we just introduced about the InSAR is measure a certain event, so the surface deformation should be very large, maybe few decimeters to centimeter to few meters surface deformation. That is more easier for us to monitor it. But in like the length of subsidence, the deformation is quite slow, so we need to use, like here we will introduce you, is a time series approach. Okay, here is should be changed. I forgot. Okay, oops. Okay, and these methods have two major components. First is persistent scatter InSAR. Some people will call it PS, or some people will call it PSI, and so on. But the first developed list is Flaherty in the 2000 and 2001. But here you will find like the trademark here. So when you use the permanent scatters in InSAR field, you must to show these icons, because he already decided that this is for them you can use. And other people right now maybe will use the persistent scatter, and it's the first to show this idea is Hooper's. I will show a little bit difference between these two methods idea and followed. And the other method is famous is small baseline subset we call spots, or some people will call SB method. And the first is Belladino, is developed in 2002. And later, like Hooper or other scientists, they try to merge these two results, become a multi-temporal InSAR. So you will read some paper, they will say, oh, it's MTI, it's multi-temporal InSAR. It's short this name. And the left side and at least two figures will show the main ideas difference. For the PSI, you will pick out we call the strong signals from the surface. So we will pick this. Originally, the signal is very noise. And other if you introduce the spots, the idea is different. They hope use a lot of interferometry to get the good result. So here we go about the time series InSAR. First, we'll talk about PS method. For the PS methods, they want to find out the pixel, the good pixel, but actually, mostly the pixels in one pixels, they have a lot of the, we call this like the first on surface. They will move into action. When they move into actions, the reback signal will increase or decrease. So it will make your recall like here. Your phase signal sometimes it's good, it's bad, good, bad, not like a random distribution. Okay, so it's not easy to find out which one is reliable signal or this pixel is unreliable signal. So sometimes the look angle difference maybe cause the same problem. So the scientists they found that maybe we should develop ideas about a persistent scatter. It means it is impossible we found out one pixel in the one pixel. They have a very good like the building or any like the towers. They will reflect the good signal for us, and it will be like this pixel signal. So that will help us to get very constant record in the phase and then follow with the times. So that it will help us believe this signal is good and we can use that. Okay, so in the PS methods, you will choose one master image. Its master image means every others image will correlation with he. Everybody will correlation with he, and this good master will correlate everybody get together, and this will help us not use the filter to like the multi-look or like the smooth our resolution. We can keep the original resolution. Here shows is the Tsai here, and here is a perpendicular baseline in space. So every image have their own perpendicular baselines, and they have some difference, Tsai difference. Okay. Or it's like the ascending orbit is a descending orbit. So when we choose the same master or choose the one master, and then every other image correlate with this master, so we will try to pick out some useful pixel. So here I have two different ideas. First is temporal model, and another is spatial correlation. The first used is the temporal model is from the Ferrati, and then we will introduce this first. Okay, the idea is think is about if we have a good persistent scatter layer, so its reflect amplitude must be very good. So they will measure the amplitude standard deviation and get the amplitude mean value. So the standard deviation divided by the mean amplitude, it will cause this theta. And this theta can be a threshold to pick out the pixel. They believe it is as good as like the PS scatter. So resembling the velocity of the small phase noise, they sometimes will smaller 0.25 radius. So sometimes they will found some paper will show you they will choose this threshold like 0.25, or some people will use higher 0.4. It will, if you choose the threshold higher, you select the pixel will decrease. But it's the balance because it's by your areas. So when you pick up this, we believe it is useful pixel that we will try to get the real surface deformation. So we will think about the pixel, and the pixel are very nearby. So we can remove these first two is atmospheric delay and the orbit, because they are very close. So these two components should be like the same. So they are maybe not in. So between these two PS points, they have the same effect and then the same orbit effect. So we can use the minus each other and remove that. But we still have a residual. The residual maybe including the deformation and the topography effect. So we can use the model to calculate the difference between these 2 points. So when we just let deformation component and the topographic components, we can calculate the phase, the movement, and know how movement between these 2 points. Here is the time, how the movement. So we can pick a linear regression like here. And at the same time, we can measure about our perpendicular effect, because we have the baseline. So we can remove the topography effect too. So let's make us got the interferometry result, like we call is the PSI result. Here is good example in the San Francisco Bay Area. Yeah, you found the subdeformation is from 11 millimeter per year to negative 30 millimeter per year. And in the, like here say, a lot of city areas is quite good for monitoring. However, you will find some place like in the rural areas, like not in the town, not in the city. It's very close city, but a little bit far from the city. We don't have too much pixel that we can use, because this method we call permanent scatter method is really good for big city, or really good for many building areas, because you can get quite a good amplitude. But in some place, the amplitude not good enough. You have some problem, because you can select this pixel. Maybe this pixel could be a good persistent scatter. So that's why a few years after Hooper and so on, they support a new idea is should be thinking about spatial correlation. So we not only just think about amplitude, which is temporal. Keep in the temporal is good pixel. We will choose that is correct, but we will think about maybe some spatial correlation with the pixels. We should be pick up them together. So it's rely on the correlation in space. They develop a software is called STEMS. Okay, in STEMS this algorithm, they just think all the pixel should be including this component, so on before I present. But if in a high correlation in the spatial, the deformation should be like the same. The atmospheric effect should be the same. The orbital should be the same. Effect should be the same. The correlation topography effect should be the same. The noise should be the same. Something should be different is uncorrelation in the space is topography. So they will first you choose like the radius, maybe like 5 meters, 500 meters, and then choose a lot of the pixel and use the low pass filter in this 5 meters radius to pick up some pixels that should be correlated with the topography, and then you will this uncorrelated of the topographies of the pixel, they should be related with the perpendicular baseline, and then with the linear regressions, the relationship, so that we can pick out, or say we can pick this pixel too. Just not only the preview, I say use the amplitude, we can pick out a lot of pixel. Yeah, this is quite good. In the Tsai series, there's a good persistent scatter. There's good PS point, but sometimes some point is not good PS point. It's due to by the topography's effect. Yeah, it's not the in the spatial, but it is in the Tsai. So we will pick these two, and then we will find out these pixels in whole Tsai. They should be constants that we can choose this PS. So relative varieties makes you hopefully think more about we call it strategy. So help us can pick out more pixels. So here is his result in the volcanoes area. Yeah, they will show you Tsai series how the volcanoes movement. And the most important thing is different with the permanent scatter is it not use a model or like the surface model. It didn't to calculate that. It just can use the pixel between two pixel relationship in spatials, and then calculate their surface deformation. So you don't found that some like linear behaviors, some like the circles behavior. You can pick them very clearly. So sometimes we like our lens subsidence because mostly the lens subsidence, the behavior is like the ball. Yeah, so it's like the shape is most like the circle. So the third part is about the small baseline. Why the small baseline will be announced, or the science should argue this matter is because in the before maybe Sentinel-1 satellite, just like InSAR, they will launch the ERS, MVC, but these two kind of the satellite, their repeat time is 35 days. Sometimes it will longer. So for observation service is have a limitation about the time resolution, because we are waiting to load for another image, and the preview we will discuss about if these two image, the interval is too longer, it will cause some like decorrelations problem. And if these two image, the baseline is very large, it will make the look angles problems. So in the previews, people, they not too much image, but they want to increase the sampling. So they think about this idea, we call this small baseline. They don't care about how far the image pair in temporal baseline. It means these two images can be have 1 year, even more 1 year's time intervals, but their small baseline may be smaller 1 meters. It will help us to know both of these this image, they have a very similar look angle. They just have some temporal decorrelation problem, and then this will help us to get more similar signal if these two image not affected by the temporal decorrelation. So for this idea, they will build a lot of image pair, like here. It's more than 100 image pair. And if some image you plot in the temporal or spatial distribution, you will find here is time, here is the baseline. You will make like a network. And this help us to do a lot of things to try to measure the surface deformation. So they have 4 we call the regular step. The first is the interferogram will formed by the between image pair that have small perpendicular line. Sometimes we will 100 meter or 200 meter, and then the temporal it will should be less, very short. Maybe some people will say less than 3 months. But right now in the Sentinel-1, you can maybe choose the maybe one month, even 12 days, because every 6 days you will get one image. So the temporal baseline you can choose very shortened. Another is duplicator baseline. Okay, and I think you got a lot of image, but sometimes you use original face is maybe cause some maybe too noise. So we will use the multi-look, make it increase the signal ratios, make the signal is more reliable. Okay, one. I found some people have a question. I can answer the question when I finish the small baseline. Okay. And the third stage is about the phase unwrapping. Just use the traditional is in 2D. You use like the snap view to unwrap the result. But the fourth step is sometimes it's different because everybody will develop their algorithm. For the beginner is use the singular value decomposition. This is Paladino. They develop that. Unless some people will least squares, and some people will constrain least square. Yeah, like here. It's developed algorithm. You can find out this paper to read like the different method. But the idea is I want to get the time series deformation. Yeah. So such as like the newest results from the League Sparse is from the University of Leeds in the UK, and they developed a new sparse method. You can find out is Japan's, maybe it's middle of the Japan. They just compare with their result, the sparse result with the GNSS data. In this result, they fit very well. And in a small city that is here, yeah, we call the OGR city. They have some subsidence problems, so let's use the leak sparse result to monitor their time series behavior, just like a similar up down is up down behaviors. So they get all the data get together. Is the light blue is the groundwater data, and then the gray is GNSS, and then the dark blue is the InSAR data. You can find the surface deformation is followed with the groundwater behavior, and then this is tell us is this the groundwater dominant is surface deformation. So this will relate our next we'll talk about is about then subsidence behaviors. So actually we'll get back this method. In Taiwan we got it is quite good. Oh sorry, I should answer the question first. Sorry. Can we get the time series deformation from the sound for one type to another type continuous? You means you want to choose one master? and to do another. This means it's one master but relate to others time series, or you want like the sparse have a lot of master and secondary image, a lot of image pair, but with different master. But for the PS Matthew, you just choose one master. So every secondary image should be linked with this master. So for one type to another type. So I believe both of Matthew, PSI Matthew or sparse Matthew can give you the final result is like a time series movement. Yeah, so if you can use this software right now, I believe a lot of open source software like this. The Leak Sparse is open source, and the preview I say Hooper's software like Stamps is the open source software. So it depends on your location. In the city areas, we believe you use the PSI Matthew or you use the sparse Matthew, you can get quite good results because you have a lot of good PS scatter. But maybe sometimes you will try to monitor it, like the landslide in the mountain areas. Maybe you will think about use the spots. Is better than PS. It's because the environment should be good for spots for analysis. So it will depends on your area. So sometimes we will use different methods to calculate that. So next I will show you in Taiwan some case about sometimes we will use spots and sometimes we will use PS. Why we use both method? Because we want to make sure our result is consistent, not change too much. Okay, I hope I can answer your question. Okay, and then we continue to our slide. So as we know, InSAR is quite good to get a widely surface deformation, but sometimes we have faced the questions about is there any possible that we merge or we integrate this observation? Like we can integrate the InSAR data with the GPS. Is any possible that we can get InSAR data with the labeling and the fusion and new ideas data? So this is important question, and we want try to use example to introduce how we merge InSAR data and labeling data. So here is Taiwan's, and the area is central Taiwan. Here is he has a very serious land subsidence since 1916. So almost a half century. A lot in this fluvial plains, the subsidence from the coast area move to the center of the plain. So this figure will show you some serious land subsidence area in the Georgia River fluvial plain, and here is from 2006 to 2008. But at that time, we want to know how about before the 2000s. Is any possible that we can monitor the surface deformation from the coast to the central of the plains? So we select a lot of labeling data. The black point means the leveling benchmark instant before 2000, and the white means after 2000. Obviously, before the 2000, the leveling benchmark not too much, but after 2000, I think it already become a net in the Zhuoshui River fluvial plain. So our idea is any possible we use before the 2000 satellite data and increase the spatial resolution to make us have a quite good surface deformation, lens subsidence behavior. So that we use the geostatistical method. We use like the co-creaking ideas. It means every leveling point is the right value as the leveling measurement result. But between these two leveling data, we don't know how about the relationship between the spatial. So we will use the InSAR data to build up this relationship in the distance, so that we can make the subsidence map in the first period is 1993 to 1998, and then the second is 1998 to 2003. And later you will find a lot of leveling data has already built, right? Is here. And the third period is 2005 to 2008. It is, as I said, the first is coast areas have a serious lens subsidence, and it's moved to the center. So here, right now is famous, serious, sorry, not famous, serious lens subsidence area is like here. So here is another method. We use the spots because previous we use the persistent scatter. Right now we want to use it's quite good. Use the spots can monitor the lens subsidence problems. So we choose the Sentinel-1 data satellite from 2006 to 2018, almost 3 years radar image, and then we can build a time series surface deformation. The first is we choose like the 0. So from that time you can see the cumulative displacement. Yeah, it's very serious lens subsidence in the 1000 part of this plane. And then not only use the Sentinel-1, we actually select almost the whole radar image from the 1993 to the almost right now, 2021. And use different type of the satellite. You can see the migration, the subsidence migration in this fluvial plain. Yeah. And some most important issue is about public transportation security. Here is ray white. This line is our high-speed ratios. If we extract this value, follow with this high-speed ratio from the different type or different satellite image results, you can see the subsidence area is quite similar, just like a two ball in the north and the south plane. But in the last is about the Sentinel-1 is these figures. You can see the northern part is more flat, but in the southern part the gradient is still very steep. So it's right now we will help us to suggest our government maybe how to control or how to manage the groundwater pumping in both areas. But actually it should be It already have some good result because the subsidence velocity is decreased from 1990 until right now. Okay, until here is about monitoring. So we want to think about one thing is when we have a quite good observation, we want to know how to predict or how to minus the subsidence behavior. So we want to we should know about like the consolidation theory. This is by the Tsai. They developed equipment. He say like when confidence aquifers, some water is withdrawn from here. This is blue arrow, and in this aquifer, the clay will become very from a thick become thin, and then this behavior is from the thick become thin behavior. It will make a displacement, and then this displacement will reflect to the surface, so it will cause us surface deformation is up or down. So if we only follow with this equation, the H means the groundwater level, and the Z means the vertical displacements, and the SS and the KV is means parameter. SS is specific storage. KV means hydraulic conductivity, but in the vertical direction. So they like sometimes it's like a linear. So if the groundwater level up, the soil should be up or should be down. It's like this. So sometimes it's like, let me say this is the elastic behaviors. Maybe you can use like here, show you it's not. Actually, the subsidence model, they are not just elastic, they including inelastic behavior. So we actually make us the length subsidence from the inelastic behaviors, because when the groundwater recharge, they can back to original thing. They just become very thin because like the murder is the key component, is the key material in our in our layers. So when the water inside the clay rock, from the clay rock, like output to the clay water, the clay will become thin. When it happens, we will not hard use the water, recharge water to make the clay become thin as original. So that's why some people will say the length subsidence we cannot hard to reback or rebound to our original situation. So here we will focus on the elastic and the inelastic compression behavior. So in the original algorithms, we will focus on another issues about inelastic problem. So we will try to know about some parameters about here is SSKV is mean inelastic schedule specific storage. It means is indicate the inelastic behaviors parameter. So by these ideas, we will found some inelastic behavior will like the time delay. It means in the clay not directly, you say inelastic, it will directly not move. It will a little bit by the gradual, by the time, and then very slight become the thing. From the thing to the thing, not directly, or become very quick, not it is needed time to become. So this parameter for us is very useful for the groundwater simulation. So in the previous studies, we will try to use this like the surface data and like a groundwater data, and then we can calculate like this parameter. Here it shows the blue is the GPS data, and the red is compaction monitoring wells. We can use follow with times, the vertical trend change, and with the groundwater level change, you can know how is the parameter, and then we can calculate its results. And not only the GPS, but sometimes we want to use like the leveling data. Is any possible to get this parameter, so that we simplify the Hoffman's algorithm. So we just want to get the theta 1 and the theta 2, this parameter. The theta 1 is indicated hydraulic conductivity, and the theta 2 is specific elastic storage parameter. So that we can use the leveling data to calculate this. But this idea should be like this. The behavior it have a time delay because it's gradual. When the groundwater up go back at original or higher than previous, but the land subsidence still continue to do the but the soil still compaction during that times. So that is help us to calculate this SSKV, and then it was similar with previous that we use the GPS to get the result. And then another part in these stations, when the here is the time. Sorry, here is and this is accumulate subsidence. This is meters displacements, and when we found is land subsided very quickly before the 2008, and then stop to gradually reduce from the 2008 to 2012, and after 2012 is not almost subsident. It's more like follow with the groundwater behaviors. So at the times we try to use the InSAR data. Here is the PSI result, and then this is our site, and then this is time series behaviors from the 2006 2008, and the red point is the GPS, and then the gray is the compaction monitoring well, and the black is the InSAR time series. And then you found this is the groundwater, and here the histogram is about the rainfall. So follow the groundwater and the rainfall, you will find every heavy rainfalls have a little bit tight lake, and then the groundwater will uplift like here. Here is our rainfall season, but after a tight lake, let's say we will find a groundwater is uplift. And follow this groundwater pattern, you will follow the GPS show the same behavior, and the compaction monitoring will show on the list. The radar image is more jump, but it show a little bit like this pattern. So we will try to use this idea to estimate the elastic parameter. So previously we can inverse the inelastic parameter. Right now we can estimate the elastic parameter, and this both parameter, hydraulic parameter, will help us to monitor our land subsidence. Of course, including other data, just like the geomaterial components, and like groundwater monitoring wells, groundwater level. And combine this data, we know in our research we have 4 aquifer and 4 aqueduct. And based on these materials and this is geologic settings, and the groundwater's monitoring leveling, we can build the groundwater level first. It's different layers, and you should be check your result is reliable. So we will check our relationship with the top side of the plant, and if it is possible that their behavior is follow with the geomaterials characteristic, like the blue is means the gravel, the size is very big, and the green is mean cross sand, a little bit small than gravel, and gravel, and then the yellow is means the fine sand, and then the or brown color is means the mud, or we call it clay. So in the layer 1 we not find good correlation, but in the layer 2 you can find here should be like a good groundwater path in the borehole 2 to borehole 5, but in the borehole 2 to borehole 5 you not found a good correlation, because it means the water should not pass through this area. This means maybe this groundwater have by the this small point is the groundwater. Sorry, the pumping water locations. So it should be like the wall have a serious pumping. But if we go to the layer 3, here is good path, and here show the quite good correlations. And in the 4th, they not too much maybe relate with the material, is be based on the distant relationship is far away from the top of the plane. The correlation should be low. Very more close to the top of the plane, the correlation should be high. So measure this groundwater and the material and our observation data. We will try to build a hydraulic head change. So the case is we just use the coast areas and then choose this pumping well, and then we simulate, do the groundwater pumping 30 years, and then we will try to simulate the surface deformation. And this is our result. The right side is our simulation result, and then the left side is from the 1992 to 2010 the cumulative displacement by the leveling data space. You can find the location is almost the same, and the quantity is very close. Here it should be like the meters 1 meter surface deformations, and then here is near the 1 meter surface deformations, and so on. So that is help us to do some groundwater management, and it will help us reduce our subsurface problem. And during this course, I just will finish here, and I just want to tell everybody it's the land subsidence sometimes will happen in the nature, because most is happen on the sedimentary environments. So we call it nature's subsidence. But a lot of result is caused by the people to use groundwater and then make land subsidence. But however, as we know, in the materials, they have some elastic behaviors. So how to recharge these soft groundwaters in that we can control. It means we not make this like the clay become inelastic behavior. It make us it make this permanent deformation, so it never come back. But if we just use the groundwater, but it's controlled by in the elastic behaviors. It means when maybe like the rainfall or wet season, the groundwater will recharge, and then your surface will come back to the original elevation. So sometimes you monitor the surface deformation, you find up, down, up, down. It will be more safe for like the surface deformation areas, because like in the serious land subsided areas. So our observation can help us manage and it can help us monitor it. And the most important should be give our governments or suggest them how to manage this area, how to manage, how to limitations about the groundwater withdrawal, groundwater pumping. So here I will stop here. So if anybody have a question, please write down in the message. I will try to respond your question. Thank you.
So thank you, Dr. Lu. It's a very practical and valuable lecture.
Thank you.
So now is our question section now. So if anyone have any question for Dr. Lu, please do not hesitate, just raise your hand, or you can write your question in the chat box. So anyone has question? So if no, Mengzhe, is the quiz time or?
Okay, by the way, thank you everyone. Join our course to the end. Yeah, thank you everybody.
Thank you everyone. Thank you.
So here is the quiz. So please write down your answer. And thanks for all the audience. Thank you.
Everyone, next week is the final presentation and the final quiz. If you have interest in to make a final presentation, you can write down your abstract to the Google form, and we will contact you.